Hey there, let's pick up where we left off, and that is talking about physical and chemical changes. So physical change only alters the state or appearance of a substance, but not what it's made out of. So the state, remember the state of matter, we had solid, liquid, gas, okay? So it's either changing that or how it appears, how it looks. The atoms or molecules that make up that substance do not change their identity. If we start with hydrogen, it's going to remain hydrogen. It's just going to change its state of matter. So here we have an example using water. So we're going to heat up this water. And so at first we have liquid water, which is represented by this circle here. And take a look at this. This is a chemical equation, a very basic one. Because we're not adding anything here. In fact, we're just going from one substance to another. So a chemical reaction will help describe what is occurring in what you're observing here. And so usually it's a chemical A plus a chemical B, and then that would make two different chemicals. Well, here we don't see any plus sign. So we have water, which we recognize, and then this is a lowercase l in parentheses, and that stands for liquid. So you always want to look for those in parentheses next to those formulas. It's giving you a lot of information that you can follow to the other side. This is called a yield arrow, like you yield in traffic. And that's the equivalent of an equal sign in a math class. So in chemistry, the yield arrow points to what you're making. So I have H2O here as well. So I didn't make anything new. It's still water. But I have a G here in parentheses. And so that G is referring to gas. And so kind of zooming in on the steam of this picture, we could see the water molecules are still intact, but they're just further apart and they have those blur energy marks to them because gas particles will be moving faster, bouncing around the container, and then as they leave this container, spreading out because of that energy versus the liquid. Okay, a chemical change is when you are changing the chemical. You're going from one chemical to a completely different one in some type of reaction. Now let's take a look at this. So we have an iron nail. We all know that iron will rust. Rust is a chemical reaction. So well, let's look at this reaction here. So the 4, we don't have to, the 3 and the 2, we don't have to focus on those numbers right now. Right now, let's just look at the substance. So I'm starting with iron here by itself. I'm adding, this one has a plus sign, and that's oxygen. Oxygen exists as a paired molecule. It won't exist as just O. That's very reactive. So it will link up with another atom and become O2. So I have some molecules of O2. Then they react. Here's my yield arrow, and look what I'm getting. Now the iron and the oxygen are stuck together, and I have more numbers there, but the point is there's no plus sign separating them anymore. They are now one thing. That's the chemical formula for rust. It's called iron oxide. Okay, now let's look at the pictures. So we zoom in on this grayer spot here of the nail where there's still pure iron there, and this is what iron looks like. And you'll recognize that cube structure from one of the models that I shared with you yesterday. So that is how iron and other metals can form these crystal structures. Now when I take a look at the other picture, now we've incorporated oxygen into this structure, and you can see it's completely different. And so that's focusing on this rust portion here. So because we have a chemical change here, the atoms were rearranged. We transformed the original substance into something new. So rusting is an example of a chemical change. Here are some more examples I'd like to go through with you. So the first one, we have dry ice. So that's always fun stuff to play with if you've ever been around some dry ice. If not, I will see if I can bring some in. It's always a fun little demo session with that. So anyway, we have dry ice here. Its formula is carbon dioxide. You're breathing dry ice chemical out all the time. We breathe out carbon dioxide. To make it dry ice, we have to take it and push it really down, so high pressure, and also chill it, so low temperature, high pressure, and we can make dry ice, just by compressing that gas. So let's look at the formula. I know it's a little small here, but let's take a look. So CO2, carbon di for 2, oxide, 2 oxygen, and we see that it's an S. So the S is solid. It's a big block there. And then we see a yield arrow. We don't have a plus sign there, so it's just going to its same formula, CO2. But now we have the G for gas. Let's look at the two pictures of the molecules. For carbon dioxide, we see they're all kind of clumped together in what looks like, again, a crystal structure, like our iron did. And now as a gas, we have those blur motion lines again, and we can see a little better now the C, which is black here, and O2, so 2 O's. Remember, those are red. So because it still remained the same formula, even though it looks different here, they're just kind of clumped together. If you want to think ice, it has an organized structure. It's a solid, so all the particles are very close to each other. And then all we did here was separate them. They're the same makeup. We didn't add anything in my reaction up here, so that is a physical state change or a physical change. Okay, let's take a look at the next one. So we have some sugar, solid sugar. Again, an ordered arrangement. It's a repeating looking pattern. So you can see it, the pattern there. So we take our solid sugar and we add some water to it. And so now it's going to mix in the water and we're going to make a mixture. So we don't have a plus sign here because when you make a mixture, you're not adding that chemical and having it react with anything. So take a look at what we have here. This is the formula for table sugar, which is called sucrose. It's a pretty big molecule. We're told it's a solid. And then we have our yield arrow here. Here's the same formula. You don't have to be familiar with them. You just have to be able to check from left to right, did it change? 12 carbon here, 12 carbon there, no change. 22 hydrogen, 22 hydrogen again, that didn't change. Then I have 11 oxygen, and finally 11 oxygen here. So the chemical remained the same. But it went from an S solid to, whoa, what's this? AQ. We have solid, liquid, and gas state. What the heck is AQ? AQ is a special case scenario. And so that's when we are dissolving something in water. When we dissolve something in water, it's interacting and it's breaking down, but we use a special symbol, the AQ, for that because water is so widely used to dissolve many hundreds of thousands of chemicals. It's called the universal solvent. A solvent is what you use to dissolve something. So water is very commonly used. We call it the universal solvent. So it has its own symbol. Instead of saying plus water all the time, we could just say AQ. That is in reference to the word aqueous, which means water. So whenever you see AQ, that's a mixture, and it's understood to be with water. And so we see the dissolved sugar. There are these big molecules here of all three colors, white, red, and black. And then we see the tiny little water molecules that are snuck in between them and pulled them apart. When you have dissolving, that's what's happening. You have our solid particle, which is really compact of many molecules, and the water kind of gets in between those air pockets and starts to pull them out. Once you don't see it anymore, it's dissolved, but it's still there. It's just very small. Okay, so that's a physical change. This last one is going to be a chemical change. Let's take a look. We're starting with propane. Here's the chemical formula. It's made of carbon and hydrogen. We call molecules like this hydrocarbons, and they are all fuels. They easily burn. This is one called propane. It has 3 carbon atoms. It's a gas. This is all at room temperature, gas. And so this is what it looks like in the tank. Okay, 3 carbons for each, 3 little black dots, and 8 white ones for hydrogen for each little clump here. Okay, we're adding oxygen. There's a plus sign. Oxygen's a gas, doesn't matter what the number in front. Okay, and then let's take a look at the other side of the arrow. CO2 is forming. We didn't have that on the left side of the arrow. We didn't start with any CO2. This is new. We just made this. So that's a chemical change. And then the water confirms that. We didn't have any water to start with on the left side of the arrow. Now we have water on the right side of the arrow. That's a new substance. This is a chemical change. Okay? When you have a hydrocarbon, and we'll go over types of reactions, but just to kind of, make you be able to relate to this, any kind of hydrocarbon. Another one that you're familiar with is gasoline. Gasoline has 8 carbons instead of propane with its 3. Regardless, it has carbon and hydrogen, and that's it. When you react it with oxygen in the car's engine, it's going to form carbon dioxide and water vapor, which is the gas. So this is called a combustion reaction, and they all have this same format. The only thing that's going to change is your hydrocarbon molecule in the front. They all burn. When you have a hydrocarbon, something with carbon and hydrogen, and you add oxygen to it, that's burning it, and you'll always get CO2 and water as a product. And we could see those two molecules here in this new picture. Definitely different from our first picture. Chemical change. All right, those are changes. Now let's talk about properties. So this is just of the material as we're observing it. It's not doing anything. It's just we're looking at it at a moment in time and writing down what we see, what we notice. Physical properties use your 5 senses. Okay, what are our 5 senses? We have touch, taste, smell, hearing, and seeing. So if you can describe something, whether it's a pure substance, a mixture, okay, you can describe something using your senses. It makes a popping noise. It has a sour taste. It has a rough texture. These are all examples of physical properties. They're physical if you can use your senses to describe them. A chemical property is the opposite of that, in that you can't use your senses to determine it. It's something to do with a chemical reaction, and that's a property of that substance. So we go back to our gasoline or our propane, and the fact that it is a flammable substance, not all things are flammable, that's a chemical property. It's flammable because it can undergo a burning reaction. Okay, another example of a chemical property would be corrosiveness. Okay, so corrosiveness refers to strong chemicals that are able to basically form rust on an object quickly. So rust is usually a very slow reaction that happens over time. Things get rusty. Something is corrosive if it's added to a metal, it'll almost cause that rust instantly or very short after. So that's what the corrosive word means. Acidity is just like it sounds, it's a pH value. So if you have a pool and you check your pH in the swimming pool, or if you're, really fans of lemon juice, I like lime juice. These are acidic fruits, so they have an acidity to them. That's a chemical property. Then lastly, we have toxicity. This is not a complete list, but it's a pretty good size list. There are also other terms that would fall under chemical properties. So let's take a look at this question that you have in your note packet. The diagram on the left, you see at the far left there, it does not have a letter under it. That's our starting picture. So we're told that this represents liquid water in a pan. Which of the three diagrams, A, B, or C, would show the water molecules after they've been vaporized by boiling? Okay, so take a second, look at those pictures very carefully. All right, your choice here would be A. And the reasoning for that is you would say, okay, what's the action that's happening in this case? They're talking about it boiling. Boiling is going from a liquid to a gas but keeping the same chemical formula. So that's a physical change, which means whatever picture I start with, each separate picture is a molecule. I should see that picture again. Liquids are lower temperature, so the particles are expected to be closer, whereas a gas, they're further apart. And so again, you don't have to know these chemicals and be familiar with them, but you're looking for the patterns to help you see what's going on. B would be a chemical change, and C is just nuclear. I don't know what's happening with C. That's very reactive and wouldn't last long. It would turn into B. So otherwise, here we go. Here's an example for you on deciding whether something is a chemical or physical change or a chemical or physical property. So we're going to do both with the table you see on the right. Determine whether each change is physical or chemical, and then what type of property is demonstrated. So we're going to go through each one of these separately. Take a minute, pause the video, try to answer them the best you can. Put a C if you think it's chemical for either change or property, and put a P if you think it's physical. And you can have the same answer for both property and change. Take a minute and think about it. Okay, we're going to go through A first. So we're told that we have rubbing alcohol, common chemical. You probably have it somewhere around you right now. And it's going to evaporate. So we have to think of the word evaporation. What is evaporation? When something goes from a liquid to a gas, it evaporates. So rubbing alcohol has this tendency to evaporate at room temperature. If you spill some and wait a little while, it'll eventually disappear, the puddle. So this is a physical change. It didn't disappear, it's just now in the air of the room that you're in. So this would be a physical property. The actual change of it going from liquid to gas is a physical change because I kept the same molecule. It's still rubbing alcohol. It's just floating around in the air. Okay, B. So we're burning lamp oil. Whenever you see these key words here, those will be huge red flags to help you decide what is what. Burning is always chemical. Whenever you burn something, it's a chemical reaction. You're adding oxygen to it. That's the definition. So once you see the word burning, that's chemical. So what do we have here? We have the lamp oil, which is its own chemical. That's a hydrocarbon as well. Reacts with oxygen to form carbon dioxide and water. That's a chemical change because it forms something new. So the flammability, which we label as the ability for something to burn, okay? So the words aren't similar in that they don't both start with B, but flammability is the name of the property. Burning is the name of the change, okay? But they are related. So this would be a chemical property. So this would be CC. For letter C, the bleaching of hair with hydrogen peroxide. So if you're familiar with bleaching hair to either change the color or just lighten it, you're interacting with the molecules that make up your hair color. Okay, the color itself, that is its own molecule. So kind of thinking through that, it's a pigment, so that means it's a color. So that molecule, the hydrogen peroxide is doing something with it because the color disappears. And so this would be a chemical property. The bleaching is a chemical change. CC again. All right, last one. Forming frost on a cold night. So let's talk about what's happening here. So we have frost. So that should make you think of ice. Okay, on a cold night. Let's perhaps think shortly into the future. We're going to have cold nights. Next morning, you go out to your car, you've got to scrape the windshield, get the ice off. Where'd that ice come from? It didn't snow. We didn't have any hail. Where'd the ice come from? So the water vapor that's in the air, the water molecules, check this out. I've got models. So our water molecules that are in the air, that's measured by humidity, which you're all familiar with now, being the summer. Okay, so the water vapor is still there, it's just not as saturated in the air when we get to colder months. but it's still there. And so the water molecules, as the temperature decreases for it being nighttime, they're moving around as a gas, they're going to start to slow down. What we have is the gas becoming a liquid on, say, your windshield, and that's condensation. Sometimes it doesn't get cold enough, and you just have a wet windshield. Use your wiper blades and it clears it. But if it's really cold, that liquid water that's on your windshield will then freeze and turn to ice. It'll get really locked in with its structure and form that crystal. So what do we have here? We have H2O, water, in the air, then becoming a liquid, and then becoming a solid. That's physical. So that's a physical change, and the ability for water to freeze is a physical property. Okay, so you may be thinking at this point, is there a case where I could have one of each, a physical property, but it's still a chemical change? And the answer to that is yes. That gets a little gray area where we can, talk about, do I describe something from this viewpoint or this viewpoint? And that's a discussion that we can have together in person. All right, we have to take a brief step away from our current topic and talk about energy. Now, in this context, this looks more like a physical science or a physics section, but we are going to relate this basic definition of energy and work to chemistry and chemicals. So to start us out, the definition of energy is the ability to do work. What is work? We all know what work is, but a science definition is work is a force that pushes across a distance. So we see the gentleman there with the hard hat on, very, dangerous environment with this box. Okay, at least he has it upright with that arrow pointing up. Okay, he's pushing this huge box the size of him across the floor. He is providing a force. The box is moving a distance. Work is being done. We have 3 different types of energy that we will talk about in this class. There are other types of energy that are beyond the scope of this class. So we're focusing on these. So kinetic energy, kinetics is the energy of movement. So particles are moving, they have kinetic energy. Potential energy is related to either the makeup, what it's made up of, that object, its molecules, its atoms, or its position. So we could say if we have like a shelf and something is up upon that shelf, it has potential energy because if it falls, it's going to apply that energy to when it hits the ground. So it has potential based on its position, and the gravity would cause it to have kinetic. Okay, we can also have potential energy in chemical bonds. So the chemical bond has potential, it will release energy if I break this bond. And lastly, thermal energy, thermal means heat, so it's the type of kinetic energy that results in heat. And so here we have an example, a 10 kilogram weight, looks like an anvil from old cartoons, is placed on top of this building. You made sure to make a perimeter and nobody's going to come out for lunch while you're going to shove this off the roof. So it has potential energy. It's just kind of dangling there on the edge. It's not moving yet, though. It's just stagnant there, but it has this potential because of gravity and its position. The potential energy slowly decreases and kinetic energy starts increasing as it's in fall. Once it hits the ground, the potential energy is 0. It's not going to move from that spot. The kinetic energy was at its maximum right before it impacted with the ground. Now it's at 0 as well. And then the thermal energy is that shock wave, and the pavement would feel a bit warm after you remove that weight if you do it quick enough. So it would give off thermal energy as well from that smack to the ground. So that's an example of all 3 types of energy in one go, but we're concerned with chemistry. So what's chemical energy? Chemical energy is the potential energy that's stored on how the atoms are arranged into molecules, how they're linked together, what shape do they make. For example, water has this, we call it a bent structure. Trying to put it where you guys can see it there, maybe up against my purple shirt. You can see it better there. the water molecule. And so it's not a straight line. It makes this, it's actually a 120-degree angle, not quite right. Okay? So we're told that the more energy that's released when a bond forms, the more stable that bond is. So we can have energy released when we make bonds and connect atoms. We can also release energy when I break a bond. So it says it requires energy here. It's a little bit of give and take, actually. So if we were to do this reaction in class, you would need earplugs and maybe some sunglasses, because based on the amounts of hydrogen and oxygen that I may have, this is going to create a lot of energy in a flash and a loud boom to make this water droplet. Okay, I'm not going to do that though, because I've set off fire alarms before, and I don't feel like doing that again. So anyway, that's a story for another day. So here we see a chemical reaction, right? We can follow along that hydrogen is here plus something else. We have oxygen. Here's our yield arrow, something new, in this case, water molecules. All right, so to surmise energy in that very brief 4-slide presentation, energy is always conserved, just like matter is conserved. We talked about that last time, the law of conservation of matter, or law of conservation of mass, it may be called as well. Same thing. We also have a law of conservation of energy. So if we have energy that's potential and then it becomes kinetic, it's going to have that same magnitude of value. It's just going in opposite directions. So we can say that energy is always conserved in physical or chemical. It's got to be accounted for. You cannot make energy out of nothing. You cannot destroy energy into nothing. Systems that have a high potential energy tend to change in a direction. This is called spontaneity, something that happens on its own. That lowers that potential energy. It's kind of a natural flow of things, and that energy would then go to the surroundings. All right, so a quick check here. What type of energy is chemical energy? You said potential, you're right. All right, on to the next thing. We have units of measurement. You had a taste of this in our lab this week. So we're going to go into a little more detail about measurement now. So what we use as a tag to describe a number value that we've measured is what we call a unit. I am a stickler with units. I have to be, because if you just give me a number as an answer, I don't know what that means. I could try to interpret it, but I don't know what your intention was. You have to put the unit there. Was that grams? Was that centimeters? Right? Every number needs a unit. The two most common unit systems that are in use are the metric system and what we use, the imperial system. The last bullet point down there is just what you'll see a lot of. We call them SI units for metric. And this is just where it came from, this group of science nerds that decide stuff. All right, here's a picture of the globe. And the ones in red are the countries that are still on imperial. 193 countries. All borders drawn up there. 193. 3 of them use imperial. 190 use metric. Who's in the group with us? Well, got to be another big superpower, right? We're America. Now, that little country there in Africa, Liberia, and then a little country over there in Asia, Myanmar, which used to be called Burma. Yeah, that's our company here. Not dissing on them, just saying. Usually when you talk about America, you don't hear Liberia and Myanmar, right? And then we've got the yellow there, and that's Britain, that's Great Britain there. And they use a little bit of both. Like, you'll buy a gallon of milk in England, but then you'll put liters of gasoline in your car. So I don't know what's going on with them. They're their own category. All right. What are the standard units or SI units? Again, that means metric. And so this is what we're going to look at. If you're measuring length, the base unit for length is the meter, and we symbolize that by a lowercase m. The base unit for mass is the kilogram, which is abbreviated kg. K for kilo and G for gram. Now in our class, our balances, our scales, they measure directly in grams. You saw that in the lab. So we're not going to be using the base unit here, which is the kilogram. It's not useful to us. That's a larger unit than a gram. You'll see that in a second. So just an example of how we'll slightly deviate from these base units. Okay, the time is recorded in seconds, so we don't use the minute. We would use seconds. Temperature is recorded in a scale called Kelvin with a capital K. The amount of something, different from grams, which is mass. The amount of a substance, it's a quantity. We use a mole. And check out this time saver. So mole is spelled M-O-E, M-O-L-E, and the symbol is M-O-L. Drop the E, huge time saver. Anyway, the last two deal more with physics. We won't be talking about luminosity or currents in this course. Okay, so we'll start with each type. So we have the meter, again, lowercase m. We can compare it to the yardstick. You saw this yesterday on the same piece of wood, just flipped. So they're not quite equal to each other. Perhaps on the yardstick side, you saw maybe some blank ends to it. It didn't quite go to the ends. And now we have a reason why. They're not quite equal to each other. And that's because there's a roughly 2.5 centimeters, so 2.5 centimeters per every 1 inch. And I say roughly because this is how the math comes out. It's not quite double, okay? So let's take a look at mass next. And so, again, the kilogram is the SI unit, but we work with grams because it's more useful for what we do. And so how do we relate that to something that you're familiar with? Well, 1 kilogram is just over 2 pounds. That's not too heavy, okay? So it's not this humongous unit. But compared to what we use on a small scale in chemistry, it is pretty big. All right, then I have to make a note here of weight. Mass and weight are not the same word. It's very important. I will mark you off if you use the word weight when you mean mass. What's the difference? Well, you can see here, the mass is defined as the amount of quantity of matter. So how many water molecules are you looking at in your sample, and how much mass, how much stuff is making up these two hydrogens and that oxygen? Okay? How much material is there? Weight has mass, but then takes into account gravity. So weight has that gravity component added to it, and we're not concerned with gravity. We're concerned with just the material in chemistry. So we will use the term mass. Whenever you put something on a balance and you read that value, that is a mass reading that you're getting. Yes, it does have gravity because we're on Earth, but what you see in the balance, it's calibrated to cancel out what gravity is equal to. Okay? You know that your weight here on Earth would be different if we went to the moon, right? So for example, you're going to weigh less on the moon. And that's because the gravitational pull on the moon is less than here on Earth. So on Earth, Earth is pulling you down more. You're going to have more of that force hitting the surface of the Earth that's measured as a greater weight. With the moon not having as intense of a gravitational pull, you're not going to have as much of a strong measure. Your weight is less. But if we were to send you to the moon, hopefully you would make it there in one piece, and so you would all have the same mass that you had on Earth as you do on the moon. And that's an example of why they're not interchangeable. Okay, time. All I'm going to say is that time, we use seconds. It's how long something takes to occur, right? Here's the definition of it. A second is defined by what we call the cesium clock. This is a radioactive element, and it's the amount of radiation events, basically radioactive decay, that happen from this element. That's just what everybody agreed on. Okay, Kelvin is what we use for temperature. So we have 3 temperature scales that we can measure temperature on. You're familiar with Fahrenheit. Celsius you're going to get familiar with. And then the last one is Kelvin. Kelvin is used in science generally because it covers a broad area of occurrences. So Kelvin covers very, very cold and very, very hot. And something's got to happen in that range. Celsius, you'll see in a second how they compare. Now, temperature is a man-made topic. Temperature is not a natural occurrence. Energy is. And so temperature was something that man made up to describe the energy and to relate it to different things. The energy of our area here versus the energy out in the south. Okay? So if we were to look at that, we could see how the temperatures would be different. But all temperature is doing is it's a measurement of how much energy movement there is around that thermometer that you're using. And we call that heat. Heat is just a nickname that means energy movement. All right. The Kelvin scale is what we call an absolute scale because it has a measurement at 0 and stops. Absolute 0 is defined as the temperature at which molecule movement stops completely. Okay? So in class, we talked about how if a molecule were a solid, so if this were ice, and this was my water molecule, that even though it's a solid, it's still kind of vibrating in place. Okay? Absolute 0 would be completely no movement. So there is no energy at all present in that molecule. You can never get there. It's theory. We can measure on the positive side of the Kelvin scale. We can be above 0, and we can use that in science experiments, but we can never get to 0 K. Also notice that there's no degree symbol with Kelvin. That's just the way we write it. Now, what does this mean? How does that relate to you so you can kind of get an idea? Well, we're not as familiar with Celsius, right? That's okay, but Fahrenheit, if you set your oven to 459, you know that's very, very hot. Okay, imagine we can make that negative. So that would be absolute 0. You wouldn't survive. Here we can look at the 3 different temperature scales right next to each other so you can get a better idea of how they relate and what the numbers mean relative to each other. So here's our 0 K. Celsius, that would read as 273, negative. Fahrenheit, that would read as negative 459. And then we stay with water, because water is just a really good example of what we can compare to each other. We all know how water behaves. So water is going to freeze at 273 degrees Kelvin. You might be saying to yourself, well, 273 is kind of a high number, right? But remember, 0 is absolutely no movement at all. And 273 is just frozen. So it's a very drastic scale for Kelvin. 0 degrees Celsius means you're frozen, right at flatline 0. And Fahrenheit's over here at 32. Unique number there. Okay, different. It's just different. Okay, we go back to boiling. You go 100 kelvins different from your freezing to your boiling, so we're at 373 Kelvin. That's just regular boiling temperature. It's really not that hot, right? 373 Kelvin. Well, in Celsius, boiling is at 100 degrees. So 0 was freezing, 100's boiling. Sounds understandable, right? You see where I'm going with this. 212 is boiling for Fahrenheit. That's a very specific number that you came up with there. Not 200, 212. Not 30, 32. Right? So that's what I mean. Fahrenheit is a different system than Celsius. but Celsius is just easier because it's on these regular intervals. Okay, here's a meme that I typically like to use here to kind of help you also put in perspective the three types of scales. With Fahrenheit, if it's 0 degrees Fahrenheit, you know it's really cold out. It's below freezing, so you know that's really cold. If it's 100 degrees Fahrenheit, you know it's really hot out that day, right? So we look at like the day temperature, and you can relate 0 to 100 in Fahrenheit. 0 in Celsius is at the freezing point, so it's warmer than 0 Fahrenheit. It's like, oh, it's pretty cold. 100 degrees Celsius, you'd be dead. Because it's boiling. You're not boiling at 100 degrees Fahrenheit. 100 degrees Celsius, you would be. Okay. Kelvin, you're dead on either side. Okay. So it's just science humor. Okay. How can we convert from one temperature scale to another? Well, of course, there's relationships here. We saw patterns just now. So Fahrenheit is 5/9 the size of Celsius. You may have seen that before. Well, that's, not as pleasant to see, I guess, 5/9. So we can look at it the other way and say, instead of solving for Fahrenheit, let's solve for Celsius. And if we write that, it's our Fahrenheit temperature subtracting 32 and then just dividing that by 1.8. Kelvin, if we were to relate that to Celsius, we typically don't go Kelvin to Fahrenheit. There's no use there. We stay, science to science terms. And so Kelvin to Celsius, we would just add the 273 difference to this Celsius value. All right, so a check. If you've been paying attention to the last couple slides, which of these three temperature scales never has a negative value? Kelvin is correct. It goes to 0, and that's the bottom. Okay, let's look at example 2. Here we're going to convert. So a sick child has a temperature of 40.00 degrees Celsius. What's that in Kelvin? Okay, this is not a useful scenario, getting a child's temperature in Kelvin, but this is just practice. Take a minute, pause the video, use the formula that you feel is appropriate, and then come on back and we'll talk about it. Okay, so let's look at how to solve this. So there is a certain way I want for you to set up math problems in chemistry, and it's just to help you see the patterns and for you to feel more confident doing the math, and it's also for me in grading so that I can see how you got to step 2 from step 1 or step 3 from step 1 and kind of follow where there could be a possible error. This is good practice. And so how I want you to set up math problems in here is to first write the formula that you're going to use. So we're going from Celsius into Kelvin. It makes sense to choose the formula from the previous slide that has both of those units in it. And so that would be this formula here. Next, we want to make sure that we're solving for K. This question's asking for K. Well, this equation's already set up as K equals and everything on the other side, so we're already there. Next, I want to see you plug in the values from that problem. So in this case, we were given Celsius as 40.00 degrees. So here we've plugged it in for that C. See how it lines up? That's how you want to show your work. And then this other part of the formula, the adding of the 273.15, just gets dropped down. Then we're going to solve the problem. So simplifying this by adding, we're going to get our final answer as 313.15 Kelvin. Okay, so let's do part B now. What's the child's temperature in Fahrenheit, that should say, not Celsius? So we were given in Celsius, right? You're going to say, oh, it's 40 degrees. That's a typo, so solve for Fahrenheit for part B. All right, so we're back to see the answer now. We're going to solve for Fahrenheit. I did say that was a bit of a typo. I've got to fix that. So find the equation we're going to use. We want something with a C and an F in it. That's this equation right here. So first step is to write that down. Next, we want to do one of two things. It depends on your algebra skill level, how confident you are with solving for different variables. If you feel pretty good with algebra, My suggestion is, before plugging in values that are given from the problem, solve the equation for the unit you're solving for. That way, you have it already set up to just plug in after that point and get your answer. There's less opportunity for algebraic error if you do this first before plugging in. I understand some of you may not like that idea, and so if you're not comfortable with that, that's fine. Plug it in as it's shown up here, and then you would do the algebra anyway. So it's whatever your comfort level is, as long as you're showing me. So what that would look like is we would have degrees Fahrenheit equal to 1.8 times our C plus 32. So we plug in our 40.00 C, and we get 104.00 degrees Fahrenheit. So remember, we had in our instrument, we had 0.00 to show the specificity, the precision of our thermometer, which that's a very precise thermometer to read that. So we want to carry that over in our answer. In this case, the sig figs for 1.8 and 32 do not count when considering what your answer will have for sig figs. The 1.8 and the 32 fall under the rule of a constant. So they have essentially unlimited numbers of sig figs. In other words, they're in a formula, ignore them. So it's just going to be the data that you use to determine how many sig figs. In this case, we have one piece of data, so it's got to be the same number of decimal points that we had for data in our answer. Last thing I'll say is 104, you better get this kid to an ER, because that's a very high fever, and if he or she starts to get warmer than that, you're looking at serious complications. So once you get around 106, 107, organs start shutting down, and so that's bad news. So 104, you're kind of near that bad level for body temperature. Get that kid to a hospital. But that's just an example, right? There's really no kid with a fever. It's fine. Let's talk about prefixes. Prefixes come in front of another term, and they're multipliers to show value. So we have the standard units, and we throw a prefix in front. Now it means multiplied by that much more. So for here we have a kilometer. We could see the word meter there. So meter is for a distance. The kilo in front tells me, in this case, kilo means 1,000 times. So we're 1,000 times greater than 1 meter and getting a kilometer. Kilo always means 1,000. So in this picture, to kind of help you get a visual, a kilogram is a very large container, 1 kilogram. 1 gram is 1/1,000th the size of a kilogram. So I shrunk it, but I had to put here, just for my own sanity, this is a relative, not actual scale. If I were really to shrink this picture of a gram to be 1,000th of the size, the picture of the kilogram, it would be so small, it would just look like a period of a sentence, and it wouldn't be helpful to the analogy. So, all right, beside that, here are all the prefixes. Hey, guess what? You don't have to memorize these. Hey, guess what else? We're not going to even use all these. We're going to use the ones that I've bracketed off to the side here. A very small portion, right? So that's good. It doesn't help us in chemistry to go super, super big, and it doesn't help us in chemistry to go super, super small either. So this is usually the biology land where things get really big, and the physics land where things get really small. And chemists are that, medium ground. So, okay, let's take a look at these prefixes. Kilo is larger, so that means 1,000. There is a term under that deca that's not shown here that means 10, but we're not going to really work with that value. There's no common need for it really in our class, so you're not going to see it often. You might see deci. We could see that that's a division from 1, so it's 1/10 the size of a base unit. So if we go back to the meter being our base, the kilometer or kilometer is 1,000 times bigger. A decimeter would be a tenth smaller than the meter. So it'd be smaller than that meter stick. A centimeter is 100 times smaller than the meter stick. And that's what the divisions were that were numbered on the meter stick. They were in centimeters. A millimeter is 1,000 times smaller than the meter. We're dividing by 1,000. 1 divided by 1,000 is 0.001. So we've divided by 1,000. We've got 1,000 little pieces for our meter. Okay, volume and density. We derive these units from other measurements. So we have combination of units. This bit here with the cubic centimeters and the liters. I don't know how, sometimes PowerPoints kind of get a little wonky, and that should actually be dropped down next to the IE there. For example, it should be down here. So the example, cubic centimeters or liters. Volume is a measurement of three-dimensional space. Okay? Density is a ratio of mass, which we defined before as the amount of material, and it's a relationship between that and the volume that it takes up. So how much stuff is in that 3D space? So we can look at this table here that shows the density of common materials that you're familiar with. Okay, we have charcoal briquettes that you use for a grill, ethanol, that's the fun alcohol, ice, we know, water, sugar, this particular sugar, table salt, glass, aluminum, and you can read down the list, see all the other common materials that you've been exposed to at some point or other. Probably not the mercury. Okay, that's toxic. So anyway, so these are the density values. Now we can use density to identify a substance. It's a property, it's a physical property of that substance where, for example, water at the liquid state is always going to have a density of 1.00. It's kind of the one that we've based all the other densities on. We had to have something to start with. And so we said, why not water? So water is 1, and then all the others are assigned from that. Ice floats on water despite it being solid because there's air pockets. And so ice density is not 1, even though it's the same molecular formula. That's why ice floats. Okay. And so we can look at these and we can compare density of one substance to another, and we can predict from that whether one substance will float or sink in the other. Let's take a look at this next worked example we're going to use. So this is the density formula, but listen out to this scenario. We have a man receiving a platinum ring from his fiancée. Before the wedding, he notices that the ring feels a little light for its size, so he's trying to second guess if it really is platinum. So the way to figure that out is to determine the density and see if it matches platinum's. The way he's going to do that is he's going to place the ring on a balance and record a mass, in this case 3.15 grams. But the ring is an odd shape. You can't measure it with a ruler and get length times width times height. So this is a little trick. For irregular shaped objects, you can have a volume of water that you have measured. So look at the graduated cylinder there on the left. We can see that that's 64 milliliters there. And then place your irregular shaped object, this case the ring, into that water level. You'll see the level rise. That's called displacement. You see it underneath the picture there. Displacement is the technique used for irregular shaped objects to get its volume. The volume of water that it moves is the volume equal to that object. So we could subtract these two volumes, the before and after, and get the volume of our ring. So here's how we'd set this up. Again, saying what you're given and assigning it that variable that goes with it is super helpful when you go to plug it in. So we're given the mass, we're given the volume, we're asked to find density. We've organized that. What's our equation? Density is mass divided by volume. Okay, now we can plug in our given values. It just becomes a division problem now. We plug the numbers into the calculator. It is important when you divide that you do it with the top entered into the calculator first. So just a caution, okay? And you're going to get 13.5. And now look at the units. We're dividing these units as well. But there's no relationship with grams and cubic centimeters. So what happens in this case is they just tag along with our number. So the unit is a fraction. It looks kind of strange, but it's because there's no other way to simplify it. And so lastly, we can say, let's compare the 13.5 we got for density to platinum. Platinum's density is found to be 21.4. So that ring is not platinum. Bum, bum, bum. Okay. Intensive and extensive properties. So these are now other branches for properties that we can use to have a collection of descriptive words. We talked about physical and chemical. These are kind of larger pools of words. So intensive is a property that doesn't matter how much of the substance you have. And take a look, I like this graphic because it highlights the eyes to help you remember one versus the other. These are kind of funny looking words. They're very close to each other, the only difference being the first two letters. So it's very often that students confuse the two. I remember having trouble keeping these two straight when I was learning this. So this is super helpful graphic to help you with that. So intensive, independent of mass. If you're independent, you don't need it. So what falls in that category? The temperature of something, it's not going to matter how much you have. The pressure you put something on, its density, the temperature that it boils, its volume, its energy. Enthalpy is Chem 2. The color it is, it's still going to be the same color whether you have a small piece or a big piece. Over on the right side, luster. If we go back to talking about that ring in the last slide, luster is shininess. So luster is a property, whether you have a small little diamond or a huge big rock, they're still going to be shiny. That property doesn't matter for mass. The hardness of the material, whether it's a solid, liquid, gas, and you can see the rest here. Malleability, I used to remember that by thinking of a mallet, so like a hammer. So malleability is defined as the property to hammer something into a big sheet. So if you imagine like aluminum foil, that can be hammered into a sheet because it has a high malleability value. That's what malleability means, mallet. The next one, ductility, is another common word. It means to be able to pull something and make a wire out of it. So if it has a high ductility, then it can easily be pulled into a wire. And so you can imagine most of our wires being copper, that the element copper would have a high ductility value. Refractive index refers to light hitting a substance and then reflecting. Reactivity is chemical reactions. Conductivity is can electricity flow through it. And then flammability is can you burn it. So those are examples that you want to familiarize yourself with. Those would be intensive. It does not matter how much of the material you have. To contradict that, we have extensive. So these do depend on how much you have. Okay, the volume of it. Notice that density has volume in its value. It's mass over volume. And density is intensive, but volume is extensive. Because when you put density together, it's the grams per volume, it's a ratio. So that ratio is going to remain consistent whether you have a small amount of grams and a small volume, or a small amount of grams and a large volume, or a large amount of grams. So you can go through all the combinations. You should still, if it's the same material, be able to reduce those fractions to the same number. So you'll always get the same density. Internal energy, kinetic energy, potential. So all the energies except for the specifics listed here. We won't talk about specifics, so don't worry about them. We'll talk about the mass, right? It's dependent on mass, that's what it is. The weight, which just factors in gravity, and then the length of something that you can measure. Depends on how much you have to measure the length, right? Just a couple more slides, we're almost done. So now we have this example. So the density of copper, we're told, decreases as the temperature increases. And it tells us that that's a commonality for density of most things. Which change occurs in a sample of copper if it's warmed from room temperature, which is 25 degrees Celsius. It's room temperature, it's about 68 degrees Fahrenheit, to 95 Celsius. So that's almost boiling temperature of water. So what do you think would happen if the density decreases as temperature increases and we increase the temperature? What will happen to our sample of copper? Take a second, look at the choices, we'll see how you did. All right, so the correct answer for this one would be that the sample expands. Lighter and heavier are going to refer to mass or weight, because we don't know if we're counting gravity or not. The expanding and the contracting, however, is how the density, so remember that's the ratio of how much mass per volume it takes up. So if you warm it up, the molecules are moving faster, and that's going to translate to them pushing more. So that's going to work on the volume component of the density ratio. And that's the end of our notes. Thank you for staying with me. You can always review other parts of this video if you wanted to go back. It's here for you. And look for the Chapter 2 one coming out in a couple days. Thank you so much. Have a great day.